This is a step 3 question from 2008. It's question number 10. It's also question 7, the last one, from the step 2 mechanics module, because apparently this topic of elasticity and stuff has been moved into step 2 since they wrote this question from step 3. So, okay, we've got a long string consisting of lots of short strings, each with a mass at the end of them. So it looks a bit like this. You've got a string with a mass at the end, with another string with a mass at the end, then another string with a mass at the end, and so on, or like this. This is how it's being modeled all the way into the bottom. And this one, apparently, at the bottom here is, we'll just call it the first one, and the nth is at the top here. So this is the first string, second one, third one, and so on, all the way up to the top. By considering the tension in the rth string, so let's just say this is the rth string here, I guess, that's TR, we'll just call the tension in the rth to be. Well, there's clearly an mg coming down. All these things are in equilibrium because they're all at rest. There's clearly an mg coming down, but there's much more than that, because then there's also the entire weight and forces, cumulative forces of all the ones below it to consider. We can't just say TR equals mg. So what we should probably do is let's start at the bottom. Let's say this is T1. And now that clearly that is just equal to mg because it's at the bottom. So we'll just say that. Now for the next one though, we'll have call it T2. Bear in mind these tensions, we always draw them just going up because we don't usually need them. But just like in a tow bar question with a caravan and a car, that tension pulls both ways like this. So here we have T2 is equal to mg coming down plus the T1 coming down that we just saw before. But T1 is just mg. So that's going to be 2mg. And then likewise, you can hopefully see the pattern as soon as you do this. T3 will be 3mg, and we'll go all the way up to TR, which will be rmg. And that will be that done. And now determine the length of the of the long string. So consider the length of this entire business here, this entire thing. Well, it's clearly just n lots of L, because NL is just the natural length plus, and there's n of them. But also then you need to add in the extension for each string every single time. Maybe the extension is the same for every single one, and you just need to add n of them, but maybe it's different. Of course, the extension is given by t equals lambda x over L. So if we rearrange that a little bit, or if we just shove the maybe the rth tension in for rmg, this is going to be the extension. If I rearrange for x, that's going to be the extension in the rth string, which means, of course, that since the extension is proportional to r, that means the extension in the first string is going to be less than the extension in the rth string, which kind of makes sense. The top one's being extended out by more because there's more stuff beneath them. So that all works. So, okay, we've got a bunch of different x's then, all slightly different to each other based on which position they are in the system. And we're going to need to add them all up. We're going to need to find the sum from the first string to the last string of all of the extensions plus just their natural length. And I was saying earlier, yeah, it's just plus NL. Well, that's where this is going to come from. When you break this out, this is now saying it's just NL plus every single individual extension that you've got, which is this one here. So yeah, clearly this, we can just bring out the constants, and then we can just apply. This one is n into n plus 1 over 2, and this one is just n, like I was saying. And I don't think I bothered to simplify this anymore because it hasn't asked us to. So that's just going to be my total length of the entire thing here. It's just going to be this. And then it says find the elastic energy. Again, we have a formula for that. It's lambda x squared over 2L. So, okay, well, we know, what do we know about this? Well, we know x, I guess, is this stuff here. So let's throw that x into there. Stuff will cancel here. L squared over L is just L. So there'll be 1L left over. And then I think the lambda squared, there'll be 1 lambda left, but on the bottom, so that will go on the bottom there. And I think everything else is square, and you'll be left with something a bit like this. So this is the elastic energy for each. Remember that x only applies to the rth string, I guess. So this is the elastic energy of the rth string, which means if I want to find the total elastic energy stored, I just need to add up all the elastic energies in all the strings. So again, I need to do the sum of this from 1 to n. And of course, all of this is just a constant, so it can be brought out. I had to look up the formula for this, obviously, because who can be bothered to memorize this? Obviously, you can, because you have a step exam to sit, but I definitely can't. And I don't think it asked me to do anything, so, it didn't really, so this is just how I left it. I couldn't be bothered. That's just how I did it. Okay, now we get to the really interesting part of the question. A uniform heavy rope, mass M, natural length LO, is just hanging vertically from rest. So it's just a single rope. And you look at this and you think, okay, so this is just a completely different question then. Let me tell you a little secret, though. Let me tell you a little secret about STEP. It's never a different question. If you're doing a second half of a question in STEP, it's never different to the first half. I mean, it is a bit different, but they did the first half for a reason, and you need to be using it. So how on earth is just a single long rope being hung from a ceiling anything like the same as a bunch of masses being held on a bunch of different ropes, N ropes? Well, what we're supposed to say here is if we just pretended that we had an infinite number of these little strings with little masses on the end, such that all of the little masses added together to make one big mass, and all of the tiny strings added together to make one long distance, then these two situations would be the same thing. So what we're going to do is we're going to say big M, sorry, is equal to n lots of little m, and LO, which is this length here, is equal to n lots of our original L, because we've got n of these strings here, or length L, as long as n is going to infinity. So we're just going to make every string tiny and just pretend that this rope essentially is being modeled as an infinite number of very small strings with very, very small masses on the end of them, all added up. And that's how we're going to do this. And that, of course, means we can use these two results, because essentially what we're going to do here to find, for example, the total length of the rope, whilst it's being extended, of course, because its own mass is extending it out a little bit, isn't it? So to do that, we're just gonna use this, but send n to infinity. So we're just going to send n to infinity here. Now, you think initially when you look at this, well, if n goes to infinity, this just becomes infinity, but it doesn't. Remember, ln, because L is also getting tiny, as ln or nl, doesn't really matter. As n goes to infinity, that by definition becomes L0, LO, right? That's what we were just saying. So this becomes LO. And then we need to try and force these two things into here as well. So, well, okay, that's just n squared plus 1. So you expand it out to get, I've written n squared very weirdly there. But the reason I've written it like that is because ln is just LO. And so is mn, that just is big M. So I can just replace those, and I get this. And then if I factorize out LO, I end up with this. Which is just, sorry, I've got rid of all the ends now, so the limit is pointless. And I get this. Unfortunately, this isn't what they asked me to get, so I need to be a bit more intelligent than this. I actually need to figure out how to make this section go away as well. And you can do that by just being a bit more intelligent with these ends. So if we go back to the top again, I'm going to expand the thing out like this again. But now I'm going to factorize out an n squared instead to leave this. And now I can make this term go away. Essentially this term here that I just lazily expanded before. If you factorize out the n instead, you can make it go away by sending n to infinity. So as n goes to infinity, this becomes a big N, this becomes a big L0, this becomes an L0, and this just turns into a 1. And then you indeed end up with exactly what you wanted to end up with when you factorize out the LO, and you get what they wanted you to get. So that's kind of cool. And now it says do the same for the elastic energy. So, okay, well, here's the elastic energy. Just going to send n to infinity. I've learnt my lesson from last time. I'm going to try and make a situation like this. So I'm just going to expand out this here. I'm going to bring the 6 out because it's obviously unnecessary. Then I'm going to expand out, well, okay, there's 1, 2, and 3 things here that could be useful. So I can take 3 n's out of this and buddy them up with the first m, the second m, and the L. And that leaves behind this, so I've just factorized out n cubed. Of course, this all turns into a 2 as n goes to infinity because these both turn into zeros. And that's a big M, that's a big M, that's an L0. And then you cancel this down, and I think that will be that. Except it won't, just last bit, it asked us for elastic energy in terms of L, L0, and lambda. And I've got a G here, and I've also got a big M. So that's not acceptable, except we have a formula, which is this thing here, the one that we just figured out, whereby I can rearrange mg, I guess. Yeah, I should have done that. I'm just thinking I didn't do that. But anyway, you can rearrange this. So if you, divide by L0, take away 1, and then times by 2 lambda and divide by g. I shouldn't have divided by g. I was being an idiot. Why did I do that? I should have just kept the g here and then just squared everything. But I didn't. I just did this and then just threw this result in here for the m. And then when you square out the g on bottom, it cancels with that g, and you're just left with this. And it hasn't asked me for it in any specific way, so I can't be bothered to do any more work. And that is the total answer. Thanks for watching, and I'll see you next time.